Okay, you try this. Cycloheptatriene is stable, and cyclopentadiene is so unstable it's almost impossible to form. Go ahead and use aromaticity to explain this, and there's a hint. You have to use resonance. The key to explaining this is looking at the resonance structure of the carbonyl, which puts the bonding pi electrons into a non-bonding pair on the oxygen. On the left you have cycloheptatriene, and you can see there are 6 electrons in that ring, so that is aromatic. On the right though, the cycloheptadiene is only has 4 electrons in it when you take the bonding electrons in the carbonyl and put them as a non-bonding pair on the oxygen. Therefore, the number of electrons indicates the stability that you get from experimental testing. And this means that the 6 electrons on the left are aromatic, the 4 electrons on the right are anti-aromatic. So which compound would undergo savolysis at a faster rate? Remember that when you have savolysis, you have the leaving group leave. So that means bromine with the electrons in the bond attached to it as a non-bonding pair that gives it the negative charge. When it leaves, it takes those electrons with it. Well, let's look here at this. For the bromine to leave, what would happen? Bromide to leave. Well, these electrons would jump onto the bromine and it would leave, leaving a positive charge behind. That gives us a secondary carbocation. That is not a bad thing to happen. It would happen at a reasonable rate, probably within 5 minutes. You would have complete reaction under favorable conditions for an SN1 reaction. If I look at this carbon is sp2 and the bromine is directly attached. That bromide is not going to leave because that would give us an sp2 anion, which is not carbocation, which is not very stable. This would not occur in any kind of reasonable time frame or under reasonable reaction conditions. If I look at this compound, I will see that if the bromide leaves, it would leave a positive charge right here, and that would make this ring then be conjugated, and we would have 4 electrons in it, anti-aromatic. It would be more likely for this compound to have the bromide leave than for this bromide to leave, because a carbocation in an sp2 with an empty sp2 orbital is more stable than an anti-aromatic system. If I look down here, I would see that if the bromide leaves, leaving a positive charge behind here on this ring, you would have a conjugated system and there would be 6 electrons. That's aromatic. So this leaves incredibly quickly. The order of savolysis rate of reaction would be number 1, number 2, number 3, and then number 4. This is the fastest compound for savolysis. Which of the following compounds has the lowest pKa? Well, the lowest pKa means the most acidic. If I look at losing a proton, what would I leave behind? A negative charge. Well, this compound would have a very high pKa because to lose a proton from it would put a negative charge in an sp2 orbital. Not too stable. if I look at this compound, if I lose just one proton from here, this is not conjugated over here. It can be stabilized through conjugation to the pi system to have a positive charge there, but you're not going to have aromaticity. Keep that in mind. This would be more acidic than the benzene. But let's see if there's something that's even more acidic than this. Okay, if I look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I lose a proton here, I would leave 2 electrons behind, which would complete the rings at 12 electrons. This would be anti-aromatic. This would be very hard to remove a proton from. So if I look at the highest pKa altogether, it would be this, followed by benzene, because it's aromatic, and removing a proton would put that negative charge into an sp2 orbital. And then this, because the positive charge left behind, the negative charge left behind, is stabilized by conjugation, but it's not an aromatic system. Now let's look at this one. There are 6 electrons here, 7, 8. And if I lose a proton, I'm going to leave behind negative charge there. That's 2 more electrons. That gives it 10. This is going to easily lose a proton. Why? Because it's going to be an aromatic anion afterwards. So this has a very low pKa. So the order of pKa's would go 1, lowest pKa, 2, next lowest, 3 for the benzene, which would be very high, and 4 for this pre-anti-aromatic carbocation, which would have the highest of all of them and extremely high. Which of the following is not a condition for aromaticity? Well, when you have an aromatic ring, it does not have to be a 6-membered ring. We've seen there are many other size rings. The molecule must have a planar system, so that is a condition for aromaticity. It must have 4n plus 2 pi electrons, and it must each atom in the ring must contribute 1 p orbital. That means it's conjugated. If one of the atoms is not in the ring, is not contributing a p orbital, it is no longer conjugated, and so it can't be aromatic. So the only condition here that is not essential for aromaticity is that it be a 6-membered ring. So which of these processes would convert 1,3,5 cycloheptatriene into an aromatic compound? Well, 1,3,5 heptatriene, before changing it into something else, has 6 electrons in it. So whatever process would be that you can't be allowing more electrons into this. You have to be taking away electrons to leave behind a carbocation. If I add an electron, that will ruin its aromaticity. If I remove an electron, that would ruin its aromaticity. If I remove a hydrogen atom, that would be forming a free radical. If I remove a proton, that leaves negative charge behind, so you're adding 2 electrons. If I remove a hydride, that removes the electrons and leaves a positive charge behind. So the way that you would have to do this is to remove a hydride. Which of the following of these resonance structures is not aromatic? So what we need to do in each of these is to look at the resonance structure as it is, not what it potentially can be, but as it is. So if I look at this one, there's 1, 2, 3, 4, 5, 6. If I look at this one, 6. If I look at this, 1, 2, 3, 4, 5, 6. If I look at this, 1, 2, 3, 4, 5, 6. If I look at this one, 1, 2, 3, 4, and theoretically there's 1 right there, 5, 6, 7. This would not be aromatic. What is the order of pKa values for the following carbon acids? Well, to look at these, we have to lose a proton. That will leave behind a negative charge. This would be just a carbanion with no stability. If I have this lose a proton, it would leave 2 electrons here, and so that would be 4 in the system, and that would be anti-aromatic, very unstable. And if I have a proton lost here, I have a negative charge here, that would give me 6 electrons total. So this one would lose its proton fastest, so it's the most acidic. Then this one, because you just have a carbanion and it's not anti-aromatic. And then last of all would be this one. It would have the highest pKa value because losing a proton would make it form an anti-aromatic compound. So number 5 is what we see. What is the most likely site that you would have a proton being added? In all these, if I add a proton here, add a proton here, add a proton here, you're going to, anywhere in the ring, you're going to cause the ring to be not conjugated. There's no special stability from that other than just pi stabilization by an adjacent pi system. But if I cause a proton to be added right here to number 1, that would put a positive charge here, and then this ring becomes aromatic. So number 1 position is what would be most likely for it to be protonated because of the stable carbocation that would form. The stable aromatic carbocation that would form. So what is the likely mechanism of the following reaction? Well, if I look at SN1, that would mean these electrons jump onto the bromine and leave a positive charge behind and an anti-aromatic carbocation. No good. So 1's not going to happen. If I look at E1, that's basic. So you would have to remove a proton, and then the bromide would have to leave, and that would put a double bond, a third double bond in the ring, which would be very, very awkward. So no, that's not going to happen. E2 is not going to happen either. E1CB is not going to happen either because that puts too many double bonds in that poor 5-membered ring. What's the only thing that would happen is SN2. Negative charge is welcome at this site because it would give an intermediate or a transition state that would have a lot of aromatic character. So as this negative charge dives in here, it would put a lot of negative charge right here that would then be stabilized by its aromatic character. So SN2 is what is most likely to occur here.